All right, let's add a new class. We call it graph. In this class, we need a private class called node with one string field, private string label. I would like to add a constructor here to quickly initialize a node object. So let's bring up the generate palette using Command and N on Mac or Control N on Windows and generate a constructor to initialize this label. There you go. Now we want to implement the add node method. So public void add node. We give it a string label. Now the first thing we want to do is to wrap this string inside the node object. So node equals new node with this label. Now we want to store this node somewhere in this graph. The easiest data structure we can use is the list. So we can declare a list of nodes and initialize it to a new instance of the array list. However, when adding a node, we want to make sure that we don't already have this node in our graph. Now, this list structure is not ideal for looking up an item because in the worst case scenario, the item we're looking for could be at the end of the list, and this can run in linear time. So here I'm going to use a hash table. Let's change this to map of string and node. So our keys are going to be strings and our values are going to be nodes. When adding a new node, we can quickly look up this item in our hash table. Now, let's replace array list with hash map. So just to refresh your memory, in Java, this map is an interface and hash map is an implementation of that interface. Okay? So here we call nodes that put if absent, we pass the label as the key and the node object as the value. So this is simpler and cleaner than having an if statement checking to see if we have this item or not. We just call this method and let the hash table take care of everything. Now let's implement the add edge method. So public void add edge. Here we need two parameters, from and to. First, we want to make sure that the arguments that are passed here are valid nodes in our graph. So let's declare a variable from node. Here we call nodes.get, and then check to see if from node is null. If it is, we're going to throw a new illegal argument exception. This is not a valid node. We got to repeat this for the other parameter. So var toNode, we call nodes.get, and then check to see if toNode is valid. Otherwise, we're going to throw a new illegal argument exception. We're almost done. Now we need an adjacency list to store the relationship between these two nodes. In this list, we should be able to quickly look up the from node. So I'm going to implement the adjacency list using a hash table. So over here, we need another private field, map of nodes to list of nodes. So our keys are going to be nodes, and each key can be mapped to a list of nodes, okay? Now, I know this implementation is slightly different from the one we talked about in the previous lesson. There I told you that we implement an adjacency list using an array of lists. But here we have a hash table of nodes. I prefer this implementation because here we are working directly with node objects rather than array indexes. This will lead us towards a more object-oriented design, as I will show you later in this section. What you need to understand is that we still have an adjacency list, not a matrix, because we're only storing the edges that exist. Our implementation is slightly different from the classic implementation in your data structures book, but it has the exact same time complexity, okay? If you implemented this using the classic approach, that's totally fine as long as your solution is working. But it's better if you follow the same approach as me, because later I will show you how to make this code more object-oriented. All right, let's move on. So we call this adjacency. It's a bit hard to spell. Adjacency list, and we initialize it to a new instance of the HashMap class. Okay? Now, once we add a node, it's good to add an entry in the adjacency list as well. Otherwise, we have to do an extra null checking in the add edge method. So here, we go to adjacency list and put if absent. We pass the node as the key and a new array list as the value. So now every node has an empty array list where we can insert the nodes it's connected to. If we don't write this line here, then we have to do a null checking in the add_edge method to make sure we don't get a null pointer exception. Okay, so back to the add_edge method. We go to our adjacency list, get this node from node. Now we get a list object. So here we can call add and then pass the target node. This is where I told you that we have to do an extra null checking. With this implementation, we can make sure that whenever we get this from node, from the adjacency list, we always get a list object. Okay? Now, here we have a unit-directed graph. If we wanted to implement a non-directed graph, we would have to add the inverse relationship. So we would duplicate this line and add another relationship from toNode to fromNode. But in this section, I'm going to go with directed graphs because they have more applications in the real world. Okay? So delete. And finally, let's implement the print method. That is super easy. Public void print. We're going to iterate over our adjacency list. So for var, let's say source, we're going to iterate in adjacency list dot keys. This will return all the source nodes. Now, for each node, we should get the target nodes. So adjacency list dot get, we go to the source, and this will return a list of nodes, right? So let's call it targets. Now, if targets is not empty, if it's not empty, then we're going to print something like this. Print, we say source is connected to plus targets. Now, when we pass this node object here, Java is going to convert it to a string. So here we should override the toString method and return the value of that node. That is super easy. So back to the node class. Here I'm going to bring up the generate palette one more time and create a toString method and return the value of this label. Now this expression is a little bit too busy. I would rather delete it and simply return the value of the label field. Next, we're going to implement the remove operations.